Alright, let's kick it off. Sweet. So sorry for the late start, but let's just get moving, I guess. So yeah, we're going to do a final review today, and pretty much what we'll talk about, it's going to be a similar structure to the midterm review that we did at the end of April or early May. And we're just going to talk about the exam structure. We'll go over the lecture content kind of at a pretty high level because now we've got a lot to get through. We'll talk about some sample problems along the way and like kind of take pit stops to do exercises, answer questions and things like that. At the end, we'll talk about a couple or a few common pitfalls that we see. I don't need to log in. Okay, sorry. That we see along the way often. Some resources to help study or just like get some more Python experience if you're interested in that, and then we'll have open discussion at the end for like we want to see a topic in more depth and we can mess around with some examples of that. But feel free to stop me throughout and just ask questions like last time too. Alright, so exam structure. I think Paul covered some of this, but there's going to be a lot of different sections. You're going to have your true, false, multiple choice, where that's going to be either choose one or choose many. There'll be short answer, and I have just a couple pieces of advice that are the same as last time, which is to be transparent about your thought process. When you write something down, explain why you got stuck somewhere and how you would like figure out a next step if you were stuck and how you'd proceed. But when you can be as precise and as clear as possible. Just makes things easier to grade, saves you time having to go explain what you were thinking during the exam, all those kind of things.
What number is this? Someone wants to know because they're
oh yeah.
346.
Somebody put that on the Slack while we're.
Yeah.
Thank you. And then there's going to be coding sections like last time. These will probably be a little more in depth than they were for the midterm. So I would say like all these points that I'm going to make like kind of go double, but make your indentation clear, but don't fret about that. Don't fret about the syntax too much. It's going to be more like, did you make the right function call? Did you use the right built-in function? Those kind of things. And then recommendations for going through that process when you're trying to code by hand is to sketch out the code structure first without trying to write everything in. Don't try to write out your code line by line by line and get it right the first time, because it's just not going to happen. It doesn't happen when we code on computers, so it's not likely to happen when we're coding by hand on pencil paper. So an example, right, if we have a class that we're writing, write out the class name, the constructors, and the methods, and then figure out, is there going to be inheritance? What attributes do I need? What other methods and arguments do I need? And then write in the bodies of those constructors, or of those methods. So, just a few tips there. So diving into some of the lecture content, we cover a lot of different built-in types and containers, and these are the ones that I feel like you should kind of know in and out by now at the end of the course. We know a lot about ints, floats, complex, floating points, and we have strings, booleans, lists, tuples, sets, and dictionaries. And I kind of put in some like unique pieces about each of these different types. Complex, the biggest thing that I have for them is that they're rarely used, but they're important to understand. They are a native type in Python, so you will come across them from time to time. Know which of these containers are iterable and what the different methods are typically used with these different containers as well. So for lists, we're appending, inserting, we're reversing, popping, all those kind of things. For the tuple, the main thing to know is that while it's indexable or sliceable like a list or a tuple, it's also immutable, right? So we can't add or remove things from that. It's the main thing to know. Which also means what about a tuple in the context of comparing different containers versus a list or a set or a dictionary. So we ran into this in one of the homeworks where we were trying to use these in a dictionary.
It's
right?
hashable.
Yes, it's hashable, right. So as opposed to a list or a set or a dictionary where they're mutable objects, the tuple is immutable, and so therefore it can have a permanent hash associated with the object itself. because for the entire lifetime of that object, it's going to be the same, and so its hash is going to be the same. That means it can be used in dictionaries as keys, which is a really key thing that we ran into in homework. I can't remember. I think it was 6 or 7. For sets, I think the important thing to know about them is that, other than the fact that they are mutable, like a list, is that they can be updated, and you can take the difference between them very, very quickly. So if you're worried about performance, or you're in some situation where you're concerned about performance, checking whether or not an object is inside of a set, or taking the difference between two different sets, is going to be much faster than using something like a list or a tuple. And dictionary is the native mapping type. And the main thing I think that'll be useful there to remember is how we iterate over those things, how we iterate over a dictionary. So if we iterate over a dictionary, if we just say for I in dict, what are we going to be iterating over? The keys, right? The keys of the dictionary. If we do the values, so if we did for I in dict.values, we're going to get the values, and if we get items, we'll get both the key and value pairs throughout the entire dictionary. So just hang on to those nuggets when the exam rolls around, and it might make your life a lot easier in writing out your code. The different built-in functions that we're mainly concerned with, Paul summarized them pretty well. Let's go back. Can I not right-click in this one? Sorry. Paul summarized them well here, which you guys have access to this because I think he linked this in his. Oh, I'm not on the Wi-Fi, am I? Chicago guest. Okay. I wonder if I still have it cached in another browser. Nope, definitely not. Let's see if I can log in, I guess, then. All right, I'll try to bring those up at the end, but I would take this is just a link to his, oh, here we go. Hang on, we'll try it. All right, let's move on. So this is just a link to a specific section of the final exam topics that he posted in his last lecture. But it covers things like, I think everybody's used range by now in the homeworks at some point, right? So sum, max, min, all these different built-in functions that are important to know when it comes time to like reading through a section of code and figuring out what the behavior of that code is going to be on the exam. So, and I'll also be posting these slides, so you'll have that link there too if you want to get to it. Other important things to track here is equality versus identity. So are my objects the same? A few different built-in functions here that are going to help you out is type. Is this an instance? And also ID. So real quick, can somebody run down like what the difference is between these three different built-in functions? Or maybe pick one and say it, and somebody else can go. Yeah.
So type is like strictly the type. So I mean that as a comparison to isInstance. So isInstance will recognize a subclass as being an instance of the superclass, where type will not.
Bingo. Yeah, absolutely. And the last one? Anyone?
So memory location?
Yeah, effectively for CPython implementations, if you call ID on an object, you're going to get the memory location. So if you want to know whether or not an object is the exact same rather than equivalent, like ID will tell you if it's the exact same object. It will also tell you, yeah, and meaning that if you pass it a name to ID, it's going to tell you if that name references the exact object, to be more clear. This was something that I think I got a few different questions about. So what is a name in Python? A name is just a reference to an object. And an object is pretty much like the base of everything in Python. So we can do things like this. We could say A is equal to the int type. And now A is just a reference to that type. So I could call A of 6 or A of 6.0 at that point and get an integer back from that call. So we can demo that real quick. If people are interested, or if they just straight up don't believe me, that's fine. And then I can do so if I execute that cell and I print my int, then we get 6. So names are just ways of effectively like aliasing types or functions or classes or what have you, and that's kind of for you to keep track of as you write the code. It's also a way when we do this as well. So we do def func x return x times x. Then we're going to see we get 36. So when we rename these things, we just have to keep track of what they actually mean underneath the hood. Is the bottom line there. Arithmetic, right? So the different operators, we're all pretty familiar with these, I think, in different languages, but every language has a different meaning, and in Python there's even more subtlety to these different operators than in most languages. So for your native types like int, float, bool, string, you'll have different behaviors for these different operations, but we have, in general, we have plus, minus, multiply. We have two different kinds of division. Can somebody rehash what the differences are between those?
True division versus floor division.
Right. So true division is going to give us a floating point, or floating point division is going to give us back a floating point value with a single slash here, and then the floor division or the integer division is going to be the double slash here. Can anybody give me what this was?
Exponents. Right,
so exponents. So if I do x star star 2, that's going to be equivalent to x squared. And then we have these, which are in-place operators as well. For comparison, we're all pretty familiar with these kind of comparisons as well. Equals, not equals, less than, greater than, less than or equals, greater than or equals. But Python also has this. So we see that in the code every once in a while where we'll say we have object name is other object or object name. But we can also do equals equals. And can somebody tell me what the difference between those two operations is?
The value versus the ID.
Right. So effectively, this is the same as calling this to check to see if these IDs are the same or not. And if I modify A and I rerun my cell, then we're going to see that the ID of A matches the ID of none. All right, so that's another example of this equality versus, what did I call it? Versus identity, right? The ID. Another thing to keep track of is which of these which of these operations work with which of the native types. So if I add two lists, is that a thing that I can do? All right, so if we take 1, 2, and 3, we're going to add 4, 5, and 6, then yeah, those lists will concatenate just fine, right? Now, if I do this, what am I going to get?
Not implemented.
All right, we're going to get an error. We're going to get a type error, essentially saying the list was trying to be multiplied by something else that it's not compatible with. So we need to keep track of that, right? If we see this in the code, we should know that that's not a valid statement in Python. However, if I multiply this list by an integer, it's going to create a new list with that list repeated 4 different times. All right? So there's some subtleties here in the native types. I think that's the biggest thing about Python to me is like there's some subtleties in the arithmetic of the native types that come with the language itself that are not so clear sometimes, and we need to remember what those are. So we covered some iterables, and another one is a generator. So a generator, remember, has a syntax that's kind of like this. We can create this object and pass it an n so that we know we get from 0 to n here. Effectively, this is a different implementation of range. And that's going to count up from 1 to n, and it's going to yield I. Yield I meaning it's going to return that value and maintain the state of that generator. So the next time that we call for the next value from the generator, that state is still there. So in other words, the state here is really just I. So we'll get 1, 2, 3, 4, 5, 6, 7, 8, all the way up to n. Once exhausted, this will raise a stop iteration. So if you are calling for the next value on it, which we can do with the built-in next, that's what you're going to get back from it. So in a situation where we want to check to see if a generator is properly formed, we'll call next on it until we get back a stop iteration. If we get something else back, then we know that something's wrong, like that generator didn't function correctly. Right? So if we're writing, in that situation, if we're writing like a try and except kind of block of code, then we know that we can look for stop iteration, and that's normal behavior, and handle that appropriately. But if we get another exception, then that's problematic. And then, yeah, it has a unique comprehension syntax, not to be confused with a tuple syntax. If you use parentheses around a comprehension like this, you're going to get a generator as opposed to a tuple. Okay, so functions. So we learned functions kind of the first time through, and they were pretty simple, and they looked something like this. We know the syntax for defining a function. We name the function. We define a set of inputs, behavior, and what it's going to return. And functions now are a little bit more rich, we'll say. So we have the syntax still defining the function, but now we know things like we can take in an arbitrarily long list of arguments. We can take in an arbitrarily long list of keyword arguments. We can provide documentation strings underneath that function as well. And if I were to, and then we can loop over all these different arguments and the keyword arguments, and if I were to print what the type of args is here, dang it, I keep clicking. If I were to print what the type of args is here, what am I going to see?
Tuple.
Tuple, right. And if I were to print the type of keyword args, what would I say? Dictionary. Nice. We also know how default args work, right? So we can provide a default, and that's automatically going to be part of essentially our keyword arguments, and this one would go to, the foo here would go to our arguments for the function. If functions don't have a return statement, they always return something, and that something is nothing, right? Or none. So just because the return isn't there doesn't mean that we don't get anything back. And these functions can also be nested, which we'll talk a little bit more about later in detail with decorators. So that's functions. We have a lot more going on there than we did at the beginning of the course. And we'll go over briefly some of the different control flow situations that we have. So we have if with the conditional, we have elif and else. So that's one form of control we have. We have whiles with a condition that tells us whether or not we're going to stop before the next iteration, and a bunch of statements. We have for loops, which allow us to go over some iterable and then execute code, and we can also unpack multiple values from that iterable in the same statement. Some of the more recent ones that we've learned are exceptions. So try, so we try to run some piece of code, and then we accept some list of exceptions or a single exception as E, meaning that we can capture that object and examine it. So we might get a specific type of exception and then want to know how it arose or what its error message is, all these different kind of things. And then we can handle that exceptional case, allowing the code to continue or having it thrown or raised to a higher level in the code. And then finally, and then the last part is finally, and this code will always be executed whether or not an exception is raised. So if an exception is raised and we handle it, or we decide to raise that exception to a higher level in the code, finally will still be executed at some point before the program exits. Any questions on that? I think the most important thing is to know what you're accepting here. Paul made a note of that in the lecture, and he does it frequently at work. It's very possible to say try and accept here with just a colon after the accept, but it's important to know, it's important to understand where that exception is coming from, which ones you think you should see there, and if you're seeing one that you aren't expecting, then it should be raised up higher in the code and dealt with differently.
Should we be memorizing like that whole exception hierarchy, or?
You mean the types of exceptions?
Yeah.
I think I wouldn't worry too much about that. Like for certain things like a generator, right, that was pretty specific that a stop iteration, right, is going to be raised from that. But I would know some of them, like type errors, value errors,
attribute.
Right, yeah, attribute errors, those kinds of things. And then we learned yet another form of control flow, which is a context manager. So this is useful because it automatically tears down an object with a predefined behavior, whether or not when either an exception is raised or the code block is completed executing. So the difference here being, here we define the behavior of that teardown underneath finally. So always do this stuff, and we can write it separately from whatever object it is. Here, that object has predefined behavior, and when this block goes out of scope, it's going to be torn down according to behavior specified in the exit method. And it will also be set up using the enter method. So it kind of takes care of those different pieces for us, which is nice. Enter just needs to exist and kind of initialize the object, similar to an empty constructor, if you will. And exit will take a few different things, telling it what the execution type is, the execution value, which is typically essentially like a failure or success error code, and a traceback, so that if something did go wrong, you can print that to the screen and show the developer or user what went wrong in that situation, and then returns true or false to say whether or not its own teardown process was successful. We're going to learn about classes. So here we have a class which is inheriting from some parent class, maybe, possibly, and pretty much all classes in Python inherit from what again? An object, right? We have class attributes, which for any instance of the class, those class attributes are going to come along with it. We have a constructor method, so our init, which with the first argument always being self, and then arguments to that constructor method that allow us to either set a new attribute on this instance or create a more complex attribute on that instance. In this case, we're calling a static method, which is make complex value, and it's going to do a whole bunch of work to create some complex attribute here that we didn't want to include in our instructor, just for clarity, or our constructor, just for clarity's sake. And we allow that,
Make complex val, you can call it with no preface, like you don't need to say self dot or a class dot.
Oh, that's an error. I think actually it should be self dot make complex val. Yeah, thank you.
And you're also missing the self in the as one of the variables in the function.
For make complex val?
Yeah.
So make complex val is a static method. So just getting to that. It's a good segue. So make complex val is a static method, meaning that it does not require the self, the first argument to be self. So it's not going to take in that instance as the first argument. And its main purpose is so that you can have standard function definition in the context of this class. So it's basically a function that, like, I don't want to leave hanging out in my namespace elsewhere because it's really specific to the class that I'm working with. So I'm going to use this decorator, this static method, to include it in the class definition and keep it there instead. And then we have class methods as well, which allows us to take in a class definition and then create a new class instance and return that as well. Typically used for creating custom constructors, so that you can have multiple constructors instead of just this init method here. All right, any questions on class layout? I'm slowing down as my heart rate's decreasing after the rush to get here, so doing good. All right.
Wait, sorry, can you explain why you have to say self.makeComplexVal R1, R2 for the third?
Right, so when self comes into init, it's bringing along with it the definition of all of the different methods and everything that's contained within that class instance. And so here, makeComplexVal, if we think about the scope, there's no makeComplexVal defined inside of this init function, and let's assume that this is the only thing in the file, so it's not going to find anything else called makeComplexVal. So the only way it can find it is as a definition on self. Right.
So static methods are set as attributes of any instance of that class. Class methods are set as attributes of the class itself.
Mhm.
Are they also set as attributes of instances of the class?
I believe so, yes. Let's find out. As I'm typing this, I'm becoming more sure that they are, but okay, so we have our test. So we're going to create one. So we know that test has from string. So let's create test. Yeah, so it has it as well.
Okay.
But I think I made a syntax error here. Ah,
So
right.
class
It
methods-
needs a string.
Class methods can be accessed two ways, from calling it on the class itself or on an instance of it, but static methods only by calling it an instance.
I believe so, yeah. Actually, sorry, the static method should also be able to be called from a class or an instance, just like a class
Oh.
method, yeah.
So then the only difference is that a class method receives the class argument?
Right, that's correct. So if we redefine this and add this static method, oof, that is some rough code style. Sorry, I'm just rushing through this. So let's look at test. So it's going to have this method that's square, and if I pass it that, it's going to act just like a regular function. I don't need to pass it anything else. But also, if I create a new test, it's going to have that method as well. And it'll act the same way.
Okay.
So these decorators allow them to get different things as they come in, right? So static method, no self, and in the class method, our first argument becomes the class definition or the class type rather than an instance of the class. Sweet. Good questions, thanks. All right.
I'm gonna go to Ryerson if anyone wants to be let in for algorithms. Then
Oh, you guys have to go to class?
We have a review session for our algorithms class, which is like overlaps with this.
Okay, cool.
It actually doesn't start till
Doesn't.
8:30, so if you guys want to stay, I can let you in at 8:30.
Yeah, no problem.
Do you know when the last two homework grades will be released?
The second and last one should be out soon, if it isn't already. I'll double check on that. And then the last one should come out on Monday. We'll try to get it out before the exam.
Sure.
But, yeah. Okay. See ya. Right, so this is kind of a recap of everything that we just talked about, but self always comes first in our class methods unless you have it decorated with a static method or class method. And class instances, so self in our Python convention and the class itself are not the same. So a little bit on inheritance. So if we inherit from another class or another type, this one being list here, and I haven't done anything else, right, to this for this class definition, we'll then create a list, and we'll create my list. If we do type of A, an empty list, what are we going to get? Right, a list. And if we do type of B, we'll see
My list.
right? And if we do is instance A compared to a list, we'll see what? True. And if we do is instance B compared to a list, we'll see
True.
nice. All right, crushed it. Sweet. That was quick. Another thing to remember that's important is if I have methods that are inherited and then overwritten by a child class, they're going to be checked in the following order, right? So if I have a child class, that method will be Python will attempt to find it on the child class. If it can't find one on the child class, it will go up to the parent and then the grandparent and so on and so forth until it runs out of those, and then it will try the object itself, and then once that's done, then it'll return that it doesn't have that attribute, an attribute error. So that's kind of a segue into the Python data model, which we've talked a lot about. Some of the special, like the Python data model essentially relies on these special methods that come with different types and objects and classes. So that when we call built-in functions like next or iter or what have you, print, it knows where to look up these methods. So for things like init, we know that when we're creating a new class, it's going to call init to create a new instance of that class by default. For representation or string, when we call print, those methods are going to be accessed. For length, it's going to have a specific way to return its own length. Contains, get item, set item, delete item are all important for these different containers that we work with. Specifically for iterators or iterables, which who can tell me the difference between an iterator and an iterable?
An iterable returns an iterator.
Close.
Iterable is any type of object that you can iterate through. An iterator is a specific iterator type object.
That's closer. So I would say that iterables are a type that you can iterate through. Iterators are something that you can iterate through many times. So essentially an iterator contains a sequence to move you through a set of data, and you can do that repeatedly. Iterables, you can do that once, but it's not guaranteed that you'll be able to do it again.
I think, did you switch the...
Did I get those switched?
I think you might have.
Yes, I did. Sorry. So flip-flop that.
Just for anybody that's watching this.
Yeah, the stream. These poor people on the
Wait,
stream.
Can you just give like an example of each of them?
Right. So a iterable would be
List or a string, or
yeah, like a list or a string or something that you could iterate over many different times. An an iterator would be something like this, I think, for I in, yeah. Where if I do so if I start executing this and I move through it, eventually we're going to get to the end and it's going to give me a stop iteration. So that's our iterator. And then if I have an iterable, we can't necessarily call next on it, right? In fact, I think Paul mentioned that it's an anti-pattern to have both of these in one object. But I can call for val in I and print that value, and I can do that again and again and again, and it's going to give me the same thing over and over. Whereas if I go back to my iterator, and I define that, we run through it once, and then I do it again, we get nothing the second time through.
Maybe this is not that important, but so I always just use repr, but I know that there's a difference between repr and string.
Yeah, for sure. So let me see if I can find a good example of that. So repr is meant to be a string representation of the object, and it's supposed to be this is supposed to be a human readable form of the object. Whereas a string is something that you would see if you had an object like I have I, or I guess we can maybe just do a quick example of that. So we have class test repr, and we're going to say that it has some value and for the string representation we'll just say it returns the value converted into a string. For this, for the representation, we're going to make something that's a little more human friendly, let's say. And then if we create one of these, and I just say this is tr. Oh shoot, I had this mixed up again, I think. Yeah. So I'll make a note of that in the Jupyter deal. So this is that makes sense actually. So this is like a console representation. Which maybe is just something that we want to be pretty concise. So let me redefine this class and create a new one. And then if we want to see the console value, which is going to be the console representation, let's say, and then when we print the class, we'll get different things. All right, so that's the takeaway. Sorry, I got those confused. Okay, other special methods that we've encountered would be hash is like the only major one that I would say kind of fits outside of these different categories, where we have all of our comparators, we have all of the operators and those kinds of things. Hash is one that tells you how to create a unique identity for that object.
Is that just stored as like a property of the object?
Yes,
Okay.
correct.
So for something that is, I mean, I'm saying the same thing, like saying something like is hashable versus is not hashable. It just means that like that, I don't know if you want to call it attribute, it doesn't exist for things like lists or mutable types.
Yeah, or it'll return and not implemented. So, all right, properties. So we have a class here, which is similar to the one that we looked at before, but now we have a couple extra things going on. So we inherit maybe from some parent class, and we have a couple class attributes. One of them with a name that tells us this is a child class, and then another one that's this conversion factor of days in a year. It has a constructor method, and it comes in and it takes this age, and we set the child's age in years on that instance. And then we have this property that is the age in days. So maybe we want to know, right, the child's age in days instead of years. And we can always get age years and set age years just by accessing that attribute directly. Here we have a property that is going to take the age in years of that child and then adjust it by the days in a year to give us the number of days. And then we have a setter here where if we want to update the age in days, then we will give that age in days, and it will take that and divide it by the days in a year and store the age in years instead. All right. So why not just store two things, because this is kind of complicated, right? Why not just store age and age days on the class instance?
It's a consistent interface for modifying a property. So if you want to do type checking, if you want to do any consistent number of checks that you'd have to implement everywhere you modify it, you can just define it in one place.
Right. That's definitely part of it, yeah, I would say. And then like another, I think you kind of alluded to that, is like, what if you have two attributes, what happens if you change age and days and you don't change age, right? Then you get this issue of having those things be in sync. And because now we just modify age days every time that it comes in and out of the class, we are able to maintain, a single value that represents both of those different things for the class. So we don't have to deal with these, us syncing those things up every time one of them changes. So we're going to go pretty in depth into decorators, because I think this was a source of a fair amount of confusion for a lot of the class over those homeworks. So decorators, property is just a specific type of decorator, along with a few others that we've seen as well, right? So we have the class method, which we talked about, the static method, and the abstract method as well. So decorators take in a function and they modify its behavior and then return a function that is intended to represent the function that was decorated, but with some modifications to it. And this is kind of the structure of a typical decorator. So on the outside we have the actual decorator. That'll be the name that we provide here, where property is property, right? And what that decorator does, it takes as an argument the function that we're decorating, so the decorated func. Then inside of that decorator, any decorator state can go here, just like we had the least recently used cache from homework 6, I think. That was maintained as state inside of our decorator, which we can access anytime we need to call this function. And then we define an inner function, which actually takes the args to our decorated function, the function that we're decorating. So the decorations, or the changes to the behavior of that function, are going to go here. So in that same example for the LRU cache, this is where we were checking that cache to see if we had previously input those values to this function so we could return the appropriate output. And then finally, typically, we're going to call the original function with the args to that function and have it operate and then return the value. So as we're defining this decorator, if you think about the process in which this is happening, we decorate a function and then we define it. And when the parser, the Python interpreter, is going through those lines of code, it's going to want to define that function and all its behavior in one step. So at this point, we've defined, it's passed off that function to the decorator, and now we're defining an internal function that's going to take in arguments that were intended for the original function. So if we return values here of that original function, then we're not going to be able to call our decorated function at that point, right? So that's why I think I got a question that was like, why don't we just return, do the behavior in the decorator, and instead of having this inner function here, just return decorated func of all these different arguments and things like that. And that's because that would be essentially returning a value, but what we want to return is a function, an altered function. So we define one inside of our decorator and return that instead. And that's what we do in our last line here. We can't return a value right now because we're just in the process of defining the function behavior. So we return the modified function instead. So we return inner. And this is kind of that whole thing with all the comments, just so it's all in one place for later if people want to look at it. So another, here's where one more formatting got me. I'll fix that up before I upload this. But so the parameterized decorator. So this essentially takes what we had in our standard decorator here and adds another level to it, where that next level is now not accepting the function, but it's accepting the parameters to our decorator. So here, we want to define a decorator that says this function is going to take in only one type. So all of the arguments that come into it, and we're assuming that this function is only taking 2 arguments, but all the arguments that come into it are going to match that type. So here we check arg1 that it's that type, and arg2 that it's that type. So we add this level of function nesting so that we get the parameters to the decorator, and then from there we can define a decorator as usual, but these parameters allow us to have some extra state that we can use to define some custom behavior that is parameter specific. So these aren't really that much different in a lot of ways. If you kind of just shell out what was there before, we have the decorator and the inner function, and then we have some behavior and we return our original function. And the only thing that's really changed is we added a level of nesting, and now we take in a parameter or multiple parameters to the decorator. And we can use those to do some extra work. Are there any questions on this so far, on decorators or parameterized decorators? All right, sweet. Yeah, so global and non-local. So these are modifiers to variables in different areas of the code. And just as a reminder, I threw in the scoping from last time where we have our local scope, or the function scope that we're working in. So if we're typing at the highest level of a file, that is our local scope. We have the enclosing scope, so the scope above the function, meaning here we're accessing the type via enclosing scope, right? Because it's actually a couple levels up in these functions. And then we have global, which is essentially as high as the Python scope goes for the code you're typing is the file that you're working in. And then even higher than that is the built-in, so everything that comes with the actual language that you're working with as well. And then we have scope modifiers. So this essentially says ignore, non-local is saying ignore the variable locally, or it's indicating that you want to use a variable that's in the enclosing scope specifically. Global is saying refer to a global variable and ignore all the other scope levels in between. So I have an example of this up here. I think, where'd you go? Oh, it's way up there. So here in this section of the notebook, we have this value. So that's at the highest level of the space that we're working in, so it's a global value. Here, we have this function that's just a print value function, and it has one name in it that's enclosing. And then we define this little function inside of it that's inner, and all it does is print value. So notice that inner itself doesn't have a local variable or a local name that's called val. And so it's going to find it elsewhere. And so we can kind of look at where it finds this thing. So first, we're going to ask it for that inner function. Oh, I need to actually execute these things, don't I? All right, there we go. So we're going to ask it for that inner function, and now if I call f, it's going to try to print val wherever it finds it. So here we have it. It's found it in the function level above, not too surprising. And then if we want to tell it, hey, skip over that enclosing scope and find the global variable instead, we can add that line that says global val. And then if we get f, that inner function, and then call it, it's going to give us global. We talked about modules, which are essentially importable pieces of Python code that allow us to reuse that code in other places. We have multiple different ways that we can import these things, and a module essentially means a file. So as soon as you import a file, you're going to be parsing through that entire file to get, even if you're just getting a piece out of it, you're going to be going through the whole thing. So you can do this by importing a module and then calling module.component in that module. You can do it via from module import a specific submodule, and you can also do from module and then name a specific submodule, import a specific class. And the thing that's nice about doing this in a compartmentalized way is in Python it's really important to protect your namespace. So remember that you can call names, you can have names reference anything virtually in Python. And so protecting what those names are and what they mean is important. So it's often good practice to either import specific submodules that you know you'll need, or even go as far as importing specific classes or objects or functions that you need, just to make sure that you don't have all these names out there that you're not sure what they are and what their purpose is. Calling them accidentally could be an issue. And it's a particular problem in the final syntax here, which is valid, but discouraged, is to say from module import everything, all the things. What comes with this is we no longer have to provide module in front of a specific object from that module. They just go into our global namespace. So for example, if I had a module that defined a function called range, the built-in function range would then be overwritten by that function, and it's gone. Right? We can get it back, obviously, restart things, and just not do it this way, but you don't know that necessarily when you're writing the code. And so if you're calling range after having imported like this with a star, it can be really difficult to figure out what's going wrong.
I assume the more popular modules avoid any sort of name conflict like that?
Absolutely, yeah, but it's not always guaranteed.
Sure.
Yeah. And another issue with that can be if you're importing, a syntax that I didn't include here is you can do import module as this, right? So you can do that. So if in the module that you're importing, they did that somewhere, if, for example, they decided to import, we decided to import matplotlib as MP, but they decided to import multiprocessing as MP.
Sure.
And then you import from them, it's going to override your name. Or there's just going to be some kind of conflict there. So it's avoided, but it still happens once in a while. Another nice thing to know is how to hide specific functionality when you're importing. So this syntax here tells us if we're executing the current file as a script, so essentially calling from the command line Python file name, it's going to pretend that it's acting like a script or an executable to Python, and then it will run whatever's underneath this conditional here, this if statement. If not, then it's going to completely ignore this. So oftentimes, if you're running if you have a script, you can still use a lot of the functionality there, the classes, the functions, what have you, inside of it, and import that as a module, as long as you contain all of the main execution inside of a main function or some function that you call underneath this block. So it can serve a dual purpose, which is nice. Let's see. So some modules that we've discussed from the open source software stack are NumPy. This is one that just handles many different types in Python. So it handles more controlled types and types that are compatible with other languages. So you'll often see it in wrappers to C and C++ for modules that do that in Python. And it also handles n-dimensional arrays. Along with that comes the fact that you can reshape these arrays, and it's important to understand, how those things work for the context of the course, and also just in general, when you're working with Python, you're inevitably going to run into this package, I would say, at this point. Pandas we saw was excellent for managing database tables. Knowing how to navigate a table is probably the most important thing there, if you come across one. Matplotlib is probably the most commonly used plotting tool in Python. We learned a little bit about it. I would just go through and review some of the functions that we used in the homework, like imshow, plot, imfigsave, or imsave. Yeah, those are the big ones there. And for unit tests, this is a framework for testing modules and classes, which is nice. So it allows you to set up these custom setup and teardowns and run all your tests with context or without context and have nice output. But for the purpose of the exam, I think it would be most important to know the control flow of the test case. So what are the steps that it goes through when it actually runs a test? What pieces of the test case are you writing on your own, and what happened automatically? Okay, so then concurrency. So we looked at a couple different modules for concurrent programming, one threading and one multiprocessing. So in threading, remember we have shared memory, but distributed work. And in multiprocessing, we get distributed memory and distributed work. So anything that you operate on in the multiprocessing is going to create a copy of it and then work on it, and then in threading, you're going to be able to share that space, which can be important for applications where you have large chunks of memory. It'd be nice to use threading so you don't have to duplicate that many times on your machine. And in multiprocessing, it's better to, sometimes better if you're working with a low memory kind of application, it's sometimes better to just go ahead and copy everything over and keep it separate. What's the advantage, I guess, of doing that? If you're copying those memory blocks to different processes, why might that be better?
Take advantage of all your cores.
So you can still do that with threading, but the main thing that it allows you to do is avoid contention for the same spaces in memory. So if we have objects where, like, let's say we just have a giant array or something like that, right? If we're using threading, it's sharing memory, and it's oftentimes the machine is going to have protection for that array in place. So if you're modifying that array, it's going to lock out all the other threads that are also trying to modify it at the same time. And then even if sometimes, depending on the object you're working with, even if you just try to access it, it'll lock out all the other threads from operating on it. So they're all kind of halting and waiting on each other and things like that. But in multiprocessing, they all have their own memory space, and so they can freely, they can freely change and alter and query these different structures without having to worry about interfering with each other. The downside is you have to copy it, and then you have to figure out how to put things together at the end. So it has to be a process where those things can operate in separate memory, but you can still kind of bring the results together and concatenate them at the end of the simulation or application.
Okay, so that idea of a queue that I certainly wrestled with a lot in the last homework, that wouldn't happen in threading. Or there would be a different way to...
There would be a different way to do it. We're actually going to look at some of that. So
just to repeat what I feel like I've heard is, so for threading with the shared memory, so it has a shared memory, and so you might use it if you were not using very much in your use case of it, but it's problematic if you are accessing your memory a lot in the actual program itself.
So in threading, threading is attractive for applications that use a lot of memory, because you don't want to have to multiprocess, but you want to be able to do many things at once. But it comes with the overhead of having to either make sure that memory is in different chunks where you're not worried about overwriting things or having the threads compete for what they're writing to at the same time. And in multiprocessing, it's nice for maybe lower memory, but also just situations where you have where you have the space to basically duplicate memory space and operate on it and then put it back together at the end. But there are definitely applications where the updating of an array relies on all of the other histories of modification to that array, and so duplicating and separating it out into different processes isn't necessarily meaningful, right? So there's kind of pros and cons. So the trade-off for multiprocessing is you have to be able to put things back together at the end in a meaningful way. And in threading, you have to take extra care to try to make sure that that the threads aren't just trying to run into each other, writing to the same memory space or protected memory space. And so you have to kind of make sure you're partitioning your memory space into sections that they can all write to. And you don't have to do that, obviously, but in order to make your code perform it, it's better to do it that way.
You mentioned there that threading was good for memory-intensive processes. Are you talking about RAM, or are you talking about the cache that's on the processor?
The RAM, or so. What you have, yeah.
So it's not so much about the size of the memory, really. It's just about how you're accessing it in the program. It would help you choose which. I mean, it kind of both, but
yeah.
It's more about how you're accessing the stuff in memory.
Right. If you could perfectly organize your memory so that each thread could access separate regions of it without interfering with each other, then yeah, that's a win for sure. It's just that's very difficult, so that's why people will often lean toward multiprocessing or something like that. It takes a lot more control and a lot more fine-grained control over the memory to do that. Cool. Any more questions on that? We're good. Okay, all right, let's go look at some concurrency examples. So we're going to do just a simple, I'm going to turn down the number of CPUs here because I actually was trying to get I was testing the video, and I did this with all my CPUs while recording the video, and it nearly crashed my machine. But I also did it with 2 more orders of magnitude of values in my array. So we should be all right. So all we're going to do here is we're going to bring in NumPy. We're going to work on 4 CPUs, and we're going to take this array, and we're going to create a random array with 10 million values, where each value is a random value between 0 and 1. Okay, so the first thing we'll do is we just want to sum all these different values, and so we're going to define a function that is a simple sum, as simple as it gets, right? We take the result, we started at 0, and for each entry in the array, we add that entry and return the result. All right, so we'll time that. It runs pretty quick. It's actually, I'm going to add 1 value. We'll get a little risky. I'd like it to be just a little bit longer than that, just to make it interesting, right? Not too long, obviously. Right, there we go. So that took about 8.5 seconds to run that. So here we're going to define, now we'll do it concurrently, and we'll start with a threading example. So the first thing that we're going to do is import threading. We'll have some threaded sum, and it's just going to take in an array, and then we're going to define a worker. All right? So this is often kind of the first thing that you see in concurrent programming is what does our work unit look like, and how many chunks of work are we going to hand out. All right, so our work unit here is just saying we're going to get the array, we're going to get some kind of, in this case, a thread ID, and I'll explain why that's important in a second. We're going to have a starting point, a stopping point, and then we're going to have an array of locations to put our result for that particular thread. So we're going to set an entry inside of our results for that thread ID, and it's going to be the sum of our little section of the array. Okay. The next thing we'll do is we'll say what is our chunk size, and so we say, all right, well, we'll just divide it up evenly and say the array size divided by the number of CPUs that we decided to use. We'll set up our threads, and remember we have to keep track of those threads because at the end we need to make sure that they're joined before we try to access information that they provided us with. And then we're going to make a space for us to put our results, and we know that that's just going to be a list that's equal to the number of CPUs that we want to use. And then for each CPU we'll create a thread with a worker and the arguments that we're going to provide to that worker, which is going to be the array that we're summing. And the thread ID we'll use here, the entry is just equal to the current iteration we're on over the number of CPUs. And then the starting point is just going to be our iteration number times the chunk size, and our stopping point is going to be essentially the beginning of the next one, so we'll just add 1 and multiply by the chunk size, and then we'll hand our results that we're going to set inside of the threads. And then as soon as we create the threads, we'll go ahead and start them, right? Which I think is an important point, and this is something that we saw every once in a while in the homework, was we would see something like this, where the thought, I think, was, here, let me get this out of here, put it down here. So we saw something like this, which is understandable, that you would say, all right, I want to create threads up here and kind of separate from the task of actually doing the work. Once I have the threads ready, I'll start the threads and I'll join the threads. But what's the issue here?
Is it going to wait for each thread to complete before it starts the next one?
Right, exactly right. It's going to wait. As soon as we call thread start, we'll call thread join, and then it's going to wait for that thread to finish before even starting the next thread.
So it still works, you're just not multi-threading them.
Exactly, yeah, you're not really doing a concurrent process. So we'll put that back up here. So as soon as we create the thread, we've defined the work it needs to do. Let's go ahead and get it running, but we need to track that thread, and so we'll add it to our list.
What happens when your array size can't be like perfectly divided by your number of CPUs?
Yeah, so I definitely made sure that wasn't happening for me here. But that was an issue in the homeworks for sure. And typically what you'll do, there's a couple ways to handle it. If you're using like a threaded pool that's mapping it out, it'll kind of figure out how to fill all the threads for you. But typically what you'll do is something like, all right, I'm going to fill everything up to here, and then my last work size would be, the args for that work would be my array, I plus 1, and then it would be everything from the current value of I up to the length of the array, and just finish it out like that. So basically, like the first set of CPUs would have equal portions of work, and then we had some remainder left over because we're not dividing exactly evenly by the number of CPUs, so we're just going to tack it onto the last thread. It's like kind of a rough way of of equaling out the workload between the threads.
Is this like a super simple version of like when people talk about load balancing?
Yeah. Yeah, that's like a poor person's load balancing, basically. All right, so sweet. So we'll define that function, and then we'll run it. We'll wait for that to go. Oh no. Float and none type. Oh, right, I broke it. Just needed to add my last CPU in there. Sweet. Okay. So we saw this took about 7 3/4 seconds to run all that, right? So it wasn't that much faster than just doing it in serial. It's a lot of extra work. So why do we think that it took longer in this case? Or not longer. Why do we think it took almost as long?
Because it's all just processor based.
No, it definitely was trying to use other processors to do the work. The issue here I think that we're running into is that it's kind of what we talked about, right? So we have an array, a NumPy array, and all of these threads are operating on the same array. And it doesn't have enough information in our worker to know exactly what parts of the array it's working on. So even though these threads are working on different chunks of the array or different parts of the array, it would probably be more efficient for us to go ahead and break up that array into different pieces first and then hand it off to a thread instead of doing it this way.
So you're not getting a copy of the array by slicing it then, or?
Right.
Okay.
Yeah. Not for the NumPy arrays.
So you're saying that they just can't, it's basically having to take turns accessing the array?
Right.
And it's just, okay.
Now that doesn't sound like the same thing as, was it the global interpreter lock? Was that what we talked about in the lecture that made this?
Yeah, so I'm not 100% on this because I wrote this an hour ago.
Okay.
But my intuition is that the NumPy array specifically has its own protection, its own lock that's protecting it from being accessed multiple times or at the same time by different threads. I can look into that and I'll reply in the Slack channel or add to the notebook before I upload it.
So if that wasn't a NumPy array and it was just a list but you had sliced it, then it would be a copy and it would theoretically work faster? Or
We could actually try that.
you don't have to if it takes a couple of minutes?
I think it'll be all right. I think. So let's turn our NumPy array into a list. We'll give it another shot. Now it's kind of hard to tell here. Let me do this, because it's kind of hard to tell how much time is actually being spent creating the list and how much time is being spent with threaded sum. But it didn't appear to change. All right, so it took a little longer, if anything, but similar, yeah. So this is an example of why threading is really nice, because let's say this array gets even bigger, and it starts to become a memory issue. Then it's we don't want to have to copy that multiple times into different processes, so instead let's go ahead and before we assign the work, we'll break it up into different chunks and then hand it off to the thread, and hopefully it'll run a little bit better.
Maybe this is just a wording thing, but I guess I'm a little confused because you keep saying that when you're threading, you're copying it, but it still can't access it.
I didn't mean to be saying that if I was. When in multiprocessing is when you're actually creating a new process and you're copying the memory space. In threading, you're operating in the same memory space. Sorry if I misspoke. Okay, So let's move on to the same concept, but in multiprocessing instead. So we'll bring in that module, and we're going to define an MPSum function. And notice that we do the same thing we did before. We're defining what our worker is going to do, so our work unit, and also the chunk size. So, as we mentioned before, we are going to need to manage our memory a little bit differently than we did last time. So here we're going to use the multiprocessing manager, and then from that manager we're going to get a queue that's going to allow us to put values into it from different processes. But other than that, it's fairly similar, where we're creating processes and adding them to a list. Our target looks the same, our arguments look the same, except for we're passing in the queue instead of our results. And then we're starting our processes right away. The processes append, and then we'll join those all at the end to make sure they're done before we try to collect results. For the last part here, we'll get all the different values from our queue and then take a look at the results. So let's define all of that fun stuff and then let it run. So here, instead of 8.5 seconds, it drops pretty quickly to 3 1/3 or so. And so it's a lot faster. So basically in this scenario, it's worth the time for us to copy this memory into different spaces so that we don't have that contention for the same location in that array, or the same array, really. It's not operating on the same location, sorry. And then once it's free to do that, it can really fly through and like do the sum, get you back the values. And
What did manager do?
I was just wondering the same thing. He mentioned
Manager?
that some people had found that, and, but I'm not one of them. And
Okay.
I really struggled with that. The for process join part really consumed my entire weekend.
Right. So
all I needed to have done was insert that line.
It's tough to see right now. So the manager is just it's short for like a shared memory manager.
Okay.
So it's saying I'm a manager that's going to give you things that will allow you to pass back and forth information between processes. So
it takes care of, like, the issue I was running into was the queue getting full.
So you were using a queue?
I was using a queue. I was not using manager.
I see.
And I mean, I don't. The trick was that I needed to start pulling things out of the queue as they got into the queue, as opposed to waiting until everything was.
Oh, okay, yeah.
So it was deadlocking on somewhere in that. So I was wondering, is manager what fixed that, or is it just a difference in our computers and operating systems and?
Yeah, I'm actually not sure. It could be possible. Like, I'm creating the queue. So did you create your queue something like this? Let's say. Like that? Or how did you get it? It was just straight from the multiprocess?
Yep.
Like that?
Or maybe it's like q.q.
Dot, like this?
Oh, there's that one too. Yeah, there's a multiprocessing queue, and then there's also a.
It seems okay with that. Oh, so it has no attribute named queue. Let's try this. Is if anything better. Yeah, I'm not sure. That may not have been your issue. This is just how I've done it in the past. I always made a manager first and then created a queue from it. So that was just what I went back to, I guess. But I can find out.
This, like, getting into this, the last one were like little error messages that Python always gave me that I ignored. Like, I had to go back and figure out what they were, otherwise this stuff wouldn't work.
Yeah.
And then also, as I was like trying to figure out what is going on with this thing, like you're looking at Stack Overflow and whatever, and it got confusing because a lot of it was because I'm running Windows, and a lot of it was, well, it runs differently in Windows than it does in and that was the first time I'd ever come across that. I just thought that was interesting, and it makes sense. I mean, because here you're getting down into the architecture of the machine, so
right.
I could see where that would happen. But it was it caught me off guard that all of a sudden operating system was an issue.
Yeah. We got a few of those things. Matplotlib 2 had a few issues as well. Certain people couldn't necessarily plot the images to make sure they were getting the right thing, that kind of stuff. So. Yeah, that particular homework had like that and the concurrency stuff at the same time, so it was like kind of a double whammy in terms of packages. All right, so that kind of wraps it up for those two different examples, but I was hoping to kind of demonstrate the difference for this use case between threading and multiprocessing. It's not always intuitive which one's going to be better, depending on the objects and the data structures you're working with. Yeah, so common pitfalls. Some of these are from last time. Some are new, but knowing the difference between getting a reference, so like making another reference to something when you're assigning a name versus a copy and versus a deep copy. Having self or class as the first argument of methods in a class. Scoping issues with decorators, I think, is going to be another pitfall here. So making sure that you understand like where things are coming into play throughout the decorator. So kind of studying these examples, and as part of the notebook, I've also included an example of that parameterized decorator that we worked with before. So if we run that, define that decorator, and then I do int add 6 and 6, it's totally happy with that. But as soon as I turn one of them into a float, it's going to tell me this function is only okay with taking integers. So that's kind of a base for playing around with doing different things with parameterized decorators. And yeah, like we just talked about, getting values back from a concurrent programmer function. I think that for this case, it's important to know how to do it in either situation, just so that if one is specifically asked for, that you know how to set up a data structure and get values back from it and read them, or add them together, whatever you need to do with them. So, all right, yeah. So this is our example from last time. So we've imported our copy module. We have a nested list, or a list of lists, and the first list is 1 and 2. The second list is 3 and 4. And then we put those in a list and we name it A. So in the first example here, what's happening? B equals A.
Referencing the name B to the object reference to my A.
Right. And so if I did ID of B and ID of A, it's going to be the same, right? If I do this, B equals A, and then I do this index over all the things.
It's going to be different, except for the objects inside of the list will still have the same memory space.
Correct. They're a shallow copy, right? So if I did ID of B equals ID of A, it's going to be false. But if I did ID of B of 0, so the first list, and ID of A of 0, it's going to be the same. So shallow copy, meaning it went to the first level and all the way down into the data structure. If I do B, what are we going to get? The same, right. So we get a... you sounded confident, yeah. Sorry for the formatting error here too. But yeah, we'll get a shallow copy here. So same thing as in this situation. And then this one, shallow copy, right? Because it's just a copy, not a deep copy. That one's pretty clear. And then the last one,
Hope it's a deep copy.
we sure hope it's a deep copy, unless we polluted our namespace by importing something with start, right? So here we would, whether we did ID B, ID A, or ID B of 0 and ID A of 0, those are going to be different things because we've made a copy all the way down.
And is that true for like if you have like a list and a list and a list, like it goes?
Correct. Yeah, it'll go all the way down. So this can be a really expensive operation too, and you'll find that sometimes like it's important to know when you need a deep copy and when you need a shallow copy, because it will do that. Same thing for inheritance of classes. If you're inheriting between different classes, if you do a shallow copy, you'll get a new class instance, but of the child class. If you do a deep copy, it's going to go all the way down through the chain. Resources. These are mostly just so that they're available when I upload this. especially because I don't think I have internet right now still. So the course topics, I would look through that and really use that as your guide to lean on. I'll try to pull this up again and see if I don't think my internet connected while we were doing all this, unfortunately. That's my only option. Sorry, I obviously don't spend a lot of time on campus. But I put a link to this really nice Python 3 cheat sheet in here. So it has like a lot of what's in these slides, but kind of condensed into a couple of different pages. It's a nice reference. Maybe not to totally lean on while you're studying, but if it's like, I can't remember what this was, but I don't feel like Googling it, you can just grab that sheet and look at it or something. And then somebody about halfway through the semester asked for more Python exercises or problems to do, and found a decent site that's called practicepython.org, and it has a lot of these kind of problems that Paul's come up with that are kind of contrived and like, but it also has the solutions for you, so you can see where things are going wrong and various levels of difficulty on those. So if you feel like just like you're kind of one of those immersive learners, and you just like need to code a lot and make the mistakes and then learn, like that's how I tend to be kind of, then that might be for you. That's all my slides, and I'm happy to like hang around and work on some examples or anything like that if we want to do that, or just like talk about a specific topic if it's still a little unclear.
I could definitely use a refresher on, he said something in class, I think when he was reviewing the midterm, when you were using like args and keyword arguments about like when you use the stars like inside and outside of the actual like definition of the function.
Mm-hmm.
Oh yeah, what the problem was that? We all got it wrong.
Yeah.
It's like two of you got this one right. Might have.
So inside and outside of the... Alright, I'm going to stop the video real quick for all you on the stream. But everything we do in the Python notebook will be uploaded as well on Canvas. And if you have any questions about that, then let me know.